In this video, we're going to talk about practical considerations for measuring S parameters that arise from the wires used to measure a device under test, or DUT. We first defined S parameters assuming that we'd need to measure some two-port network at high frequency. So our setup is that we need to measure some device under test, and that we have to attach transmission lines to port 1 and port 2 because we want to model the effect our wires have on high-frequency signals. Let's further assume that we have some fancy instrument that lets us control VS1, VS2, ZS1, and ZS2. This setup puts us in a tough spot because we can only measure the S parameters of a combined system, our DUT plus the wires we use to connect it to the instrument. That's a shame because we'd really like to know S-DUT without the wires. So let's start figuring out how to model the wire effects by defining some terms. First, these wires, along with all the adapters and connectors attached to them, are referred to as fixturing. Second, we're going to define separate sets of AB waves at the instrument and at the DUT. I gave the waves into and out of the instrument the subscript VNA, and the waves at the DUT the subscript DUT. The subscript VNA stands for Vector Network Analyzer, which is the name of the fancy instrument that I mentioned earlier. If we care about these wires, then we need to define a few more properties for them, so we assign lengths S1 and S2, and velocities V1 and V2 to them. The VNA won't know these properties in advance, so we're going to have to figure out how they affect our measurement. I'm also going to remind you that we define x equals 0 at the DUT and x equals negative S1 at the test instrument. This might look hard to model at first glance, but our work on T parameters is a huge help here. We can imagine moving our signals from DUT port 1 at the DUT here, left on the page to VNA port 1 by using T parameters of this transmission line. And similarly, we can imagine moving signals at DUT port 2 right on the page to VNA port 2 by using the T parameters of this transmission line, and in this case the variant T parameters because we're moving in a rightward direction. And we write that equation by multiplying the T parameter matrix by the DUT in this equation. To figure out what the variant T parameters are, we're going to start by finding the S parameters of a lossless line. Here I'm just going to appeal to your intuition. A matched ideal transmission line won't have any reflections, so S11 and S2 are 0. And then S12 and S21 are just going to represent waves traveling across the line. So they just delay instant signals a little bit before they leave the opposite port. And that means that the S12 and the S21 values just add some phase. We can use the S to T formulas from the last video to find the T parameters for an ideal transmission line. Because the S parameter is matrix, it turns out the variant T parameters are the same as the normal T parameters. And fortunately, both of these T parameter formulas are easy to deal with because they're a constant times the identity matrix. So we could factor out e to the jks from the first vector equation there to find the identity matrix. So substituting the T parameter values into our original formula reveals that our SVNA measurements are related to S-DUT by multiplying additional phase from the fixturing. So this complex exponential represents the total phase of our fixturing. This is pretty bad news. It means that the S parameters we measure will have an evolving phase on top of the behavior in the DUT, where the phase constantly increases with frequency because K increases with frequency. And with that constantly evolving phase, it becomes difficult to back out DUT phase behavior from this graph. So we need to find a way to remove the effect of these cables. Fortunately, the math is simple. If we can find the value of Ks, then we can cancel out the phase that we've picked up from the transmission line just by adding some phase to our measured signal. And don't forget that S1 and S2 are defined as negative numbers, so we'll add positive phase to cancel out the negative phase we've picked up from this exercise. But the problem is we don't know the length of the transmission lines in the abstract. Our VNA doesn't know how long the fixturing is because it could change every time we hook something up. However, if we attach a short at the end of each wire, we can sweep over our frequencies in order to calculate the value of Ks. One algorithm for doing so was developed originally in the days of the slotted line, and that relies on these easy to measure nulls in the VSWR pattern. By varying the drive frequency of VS1 and VS2, we change K, which in turn changes the number of periods on the standing wave pattern that are standing on the transmission line. And whenever a null in the VSWR voltage reaches VS1, we know that an integer number of half wavelengths are on the line because we're effectively seeing a short as our driving point impedance. So using that fact, if we know the frequency of two adjacent nulls, then we can find Ks as a function of frequency. That requires a few algebraic manipulations of the wave number, but I'll leave that process to the viewer to work it out. Once you know the length, then you can add phase back in and cancel out the effect of the wires. And that's kind of interesting because phase is always measured relative to some reference signal. So when we cancel out the phase introduced by the fixturing, we're effectively saying that we consider x equals 0 over here our phase reference point. That is such an important idea that it has a special vocabulary word. The point where your signal has 0 phase is called the reference plane. And by calibrating our system, we've effectively moved the reference plane from x equals minus s forward to x equals 0. So now our reference plane is x equals 0, and we're just measuring the duct parameters. By the way, the process of hooking up a short to take this measurement is called a short calibration. The fixturing also usually has a frequency response due to attenuation and resonance in imperfectly matched connectors. However, you can cancel out the frequency response of the fixturing by measuring it first. You connect the two fixtures together using wires, hooking them directly to one another in a process that's called through calibration. Once you've done that, the VNA can measure their combined frequency response and store that information to cancel it out in later measurements. Now, one detail of through calibrations is that it's very specific to the exact wires that you're using. Even screwing them in different can change the values of a through calibration. So, in summary, when you have wires connected to a device under test, you call them fixturing. Fixturing adds delay, which looks like a linear increase in phase with omega, and we calibrate that phase out with a short calibration by looking for nulls in our VSWR response. And that process of calibrating out the phase is referred to as moving the reference plane. Fixturing also has a frequency response, and we calibrate that out with a through calibration. And then vector network analyzers are the tools that sweep our frequencies around, measure S parameters, and store calibrations for us.